Welcome back to the Introduction to Statistics and Probability. Statistics plays an important role in many types of engineering problems. It allows us to develop models for designing new products. It helps us validate and improve existing models. It also assists in designing and improving production processes used to manufacture products. So what are models? We've used that word frequently, so let's define them a little more clearly. Models are a simpler approximate representation of an actual object, system, or process, or other set of interrelated conditions. Basically, they are a relationship between two or more variables. Models provide us with a tool for describing in a structured and often simpler manner something that is very complex and sometimes impossible to define exactly. An example of this would be velocity. Using models that people have created, you just have to input displacement and time, and you can solve for your velocity. Models can also provide a method for capturing and accounting for variability in the thing being modeled. This accounts for sources of variability and determines the extent to which different sources of variability affect the object, system, or process that is modeled. Variations in observations and measurements can be caused by many factors. Imperfections in a material or manufacturing process can create variations in measured properties or characteristics, which can then in turn affect the object or a system's operation. Variations in measurements can be caused by random fluctuations in the surrounding environment or energy sources within a system. Statistical and probabilistic methods allow us to factor variability into models and decision-making processes. Statistical and probabilistic methods allow us to factor variability into models and decision-making processes. We can model variation through random variables. If a parameter or characteristic of some object or system exhibits different values on successive observations or measurements, we can model it as a random variable. Let x be a random variable. We have the formula then, x equals mu plus epsilon, where mu is the constant or the average value, and epsilon is the variation noise or random disturbance. A random variable maps all outcomes of a sample space, in other words, all measurements of a specified parameter to a specific number or result. Now that we have introduced our models, let's talk about different types of them. The first type of model is a mechanistic model, which can also be called a mathematical model. This is a model that assumes that a complex system can be understood by examining the working of its individual parts and the manner in which they are connected. An example of this would be predicting when tides will occur using the laws of physics. The second type of model is called an empirical model. This is a model that is based on direct observation, measurement, and extensive data. An example of this would be observing the change of the tides over many years and constructing an empirical model that allows you to predict them, with no understanding of how the Earth, Moon, and Sun interact. Both types of models can be used in design. The procedures used to collect data play an important role in determining the validity of a statistical inference. Statistical studies are constructed to identify a cause and effect relationship that can be captured within a model. Several types of studies can be constructed to collect and analyze this data. The first is an observational or prospective study, the second is a retrospective study, and the third is designed experiments. The first type of study discussed is an observational or prospective study. This type of study watches for outcomes, such as the development of a disease, during the study period and relates this to other factors such as suspected risk or protection factors. These studies are typically defined over a specified period of time or duration. An example of this would be that one could identify smokers and non-smokers at a baseline and compare their subsequent incidence of developing heart disease over the years. This type of study has some advantages, such as data is collected in ways that attempt to minimize the impact of measurements on normal operating conditions, parameters, or characteristics that are not often considered and may be collected during observational studies. Samples collected can often be collected randomly. The next type of study we will discuss is a retrospective study. A retrospective study looks backwards and examines exposures to suspected risk or protection factors in relation to an outcome that is established at the start of the study. An example of this would be wanting to try and see who was affected by chemicals at a certain plant. Rather than following these subjects for decades, it would be more efficient to use employee health and employment records over the past 2 or 3 decades as a source of the data. Retrospective studies have several disadvantages. Some study questions may not be answerable using the existing data. Data collection procedures may be inconsistent across data sets, and sometimes data may be incomplete or important characteristics of the population or process may not have been recorded. It sometimes can be difficult to validate the data and the procedures by which it was collected, and it may also be difficult to ensure that the data is sampled randomly. The key difference between prospective and retrospective studies is that prospective happens before something happens and retrospective studies happen afterward. Designed experiments are constructed to determine the effect of varying specific parameters or factors on the operation of a process or population. They can be beneficial so you can analyze single-factor and multi-factor experiments correctly. The collected data can usually be collected in a randomized manner. When designing experiments and creating models, we have different types of variables to consider. The independent variable, or variable that can be altered or manipulated, is called the predictor variable. This would be your x variable when graphing. It is the input to a model or a function. The outcome, or a response variable, is your dependent variable, or the outcome of a model or function. To better understand this, let's look at an example. A biologist wants to understand what makes a certain plant in his greenhouse grow bigger than the others. What would he use as a response or outcome variable in this study? There are many different answers to this question. Some of them could be, he might look at the size of the leaves of the plant or the height of the plant to be able to judge that that plant is indeed bigger or in a different situation than the other plants. What predictor variables would you recommend using? Once again, there are several different answers to this question, but some of the factors that might contribute to the size of the plant would be the amount of light it is receiving, the pH of the soil, or perhaps the frequency of watering. Studies themselves can also be categorized. An enumerative study is focused on the judgment of results. It is meant to enumerate or explain, evaluate, and describe the condition that exists within the existing population. Analytic studies are focused on the improvement of the process which created the results and which will continue creating results in the future. Analytic studies are focused on the improvement of the process which created the results and which will continue creating results in the future. Analytic studies are much more difficult to validate since there are often assumptions made about the stability of factors in a particular process or population. There is an analogy of enumerative studies being similar to a pond. They don't deal with past or future, they only deal with present conditions and just want to describe what is there. The analogy continues to comparing an analytic study to a river. It is continuously flowing, incorporating past data while trying to improve the present and the future. Data is usually analyzed and described using some basic characteristics. These might include the location, which is the middle point within a range of data values, the scatter or variability, which is a measure of the extent to which data points deviate from the location, or the cluster, a group of data points that are located close to one another. Then there is the outlier, which is a data point that is significantly farther from the location that most of the other data points are located. After collecting data and running analyses, you can compile your results into visual representations which are easy to read and interpret. Some of these methods might be a dot diagram, a scatter plot, and a time series diagram. We will discuss each of these representations. First, a dot diagram can contain numerical information that is plotted as dots along an axis that covers the range of data. Multiple observations of the same value are stacked to indicate the number of identical readings. This provides a visual representation of basic data analysis and is useful for determining the effect or variation of a single factor. Note on the second graph how the duplicated values are on a separate line. A scatter diagram is an extension of the dot diagram to 2 or 3 dimensions. They are useful for examining the effect or variation of 2 or 3 factors simultaneously. These are 2-dimensional scatter diagrams, while now we incorporate the third dimension here. In a time series plot, data values are plotted as a function of time to indicate variations in a process or population over time. Time series have the advantage of being able to indicate if random variations have undergone a change over time, which may indicate some tampering of the process or population that would not be evident from something as simple as a dot diagram. This concludes the lecture on Chapter 1.